Here is a question that sounds simple but secretly underpins all of science, all of learning, and the entire project of building safe artificial intelligence. Given everything you have observed so far, what should you predict comes next? For thousands of years, philosophers argued this was hopeless. Then, in 1964, a mathematician named Ray Solomonoff wrote down an answer. A single, precise, universal rule for prediction that, given unlimited computing power, provably outpredicts every other method. We are going to build that rule from the ground up, with the actual mathematics, and see why it has become the gold standard model of an ideal mind in AI safety. We will follow 3 essays that climb a ladder of rigor. First, AIXI's intuitive explanation, which gives us the core ideas. Second, Eliezer Yudkowsky's semi-technical dialogue, which assembles the formal prediction machine and proves its key power. Third, Leon Lang's 2025 technical construction, which derives the whole thing cleanly from one assumption, complete with the central theorems. By the end, you will understand every symbol in the master equation, and why none of it is hand-waving. Post 1. An intuitive explanation of Solomonoff Induction by AIXI, building on a draft by Luke Muehlhauser. Its goal is to give us, in their words, a recipe for finding truth. Let's start where they start. The problem of induction itself. Induction is the problem of going from data to the hidden process that generated it. You come home, the cookie jar is emptier, and a chair sits by the fridge. Countless hypotheses fit. Your daughter climbed up. A tiny burglar. You ate them while sleepwalking. Each explanation is consistent with the data, yet your gut ranks some as far more plausible. The whole game of induction is to make that ranking precise. We want a function that takes observations and returns the probability of each possible explanation. To rank them, we reach for Occam's razor. Among hypotheses that fit, prefer the simplest. Here is their example. A program prints 1, 3, 5, 7. What comes next? You say 9. The rule is the odd numbers. But the polynomial shown here also fits 1, 3, 5, 7 perfectly, and then predicts 33. Both match the data. Intuition screams that 9 is the better bet. The problem is that Occam's razor is only a slogan until we can measure simplicity with a number. That is the missing piece. Solomonoff's first move is to put everything in one language. Binary. Any data, any observation, any hypothesis can be written as a string of zeros and ones. And a hypothesis, the rule that generates the data, is just a computer program. Thanks to Alan Turing, every program can be expressed as a binary input to one fixed universal Turing machine, a machine that can simulate any other. So the set of all possible hypotheses becomes the set of all possible binary programs. We have made the infinite space of explanations concrete. Now the procedure they nickname Solomonoff's lightsaber. Feed every possible program, one by one, into the universal machine. Keep every program whose output matches your data so far. Throw away the rest. What survives is the complete list of hypotheses consistent with your observations. No human creativity required. But notice the catch that will haunt us. There are infinitely many programs, and by the halting problem, we can never know which ones run forever. This procedure is uncomputable. It is an ideal, not an algorithm you can run. Among the surviving programs, which is most likely? Here is the elegant idea that becomes our prior. Imagine the true program was written by flipping a fair coin for each bit. Heads 0, tails 1. Then a program that is L bits long has probability 1/2 to the power L. Read that off the screen. The prior probability of a hypothesis H is 2 to the minus L, where L is its length in bits. An 8-bit program has probability 1/256. And crucially, every extra bit halves the probability. This is Occam's razor, finally turned into a number. Shorter is exponentially more likely. Post 2. A semi-technical introductory dialogue on Solomonoff Induction by Eliezer Yudkowsky. It is a conversation between a skeptic, Ashley, and an enthusiast, Blaine, and it does 2 things. It assembles the prior into a working prediction machine, and it proves the theorem that makes the whole idea powerful. The dialogue opens with a framing that matters for AI safety. In 1833, Edgar Allan Poe argued no machine could ever play chess because moves do not follow by necessity. He was confused about the very nature of the task. In 1950, Claude Shannon gave the algorithm for perfect chess on an infinitely fast computer. Shannon was not confused. He just lacked the hardware. The lesson: knowing how to solve a problem with unlimited computation means you finally understand the problem. Solomonoff did this for prediction itself. Everything is recast as sequence prediction. Given the start of a sequence, put a probability on the next item. 1, 3, 4, 7, 11, 18. The next is 29, a Fibonacci-like rule. Will the sun rise tomorrow becomes a sequence of ones. Even your entire life, every photon hitting your retina is one gigantic binary sequence, and prediction means putting a probability distribution over the next frame. A hypothesis, in this formalism, is simply a program that reads the sequence so far and outputs a probability for what comes next. To make this concrete, the dialogue revisits Laplace's rule of succession from the 1750s. Suppose you have seen n1s and m0s and nothing else. What is the probability the next bit is a 1? The answer on screen: n plus 1 over n plus m plus 2. See how it behaves. With no data, n and m are 0, and you get 1/2. Perfect ignorance. After 4 1s and 1 0, you get 5 7s. The plus 1 and plus 2 are the gentle pull of the prior, keeping you from ever assigning probability exactly 0 or 1. This is a single, simple hypothesis. Solomonoff will mix together all of them. Now a subtle but essential technical point. If we assign every program probability 2 to the minus its length, do those probabilities even add up to something finite? Naively, no. There are 2 programs of length 1, 4 of length 2, and so on, and the sum blows up to infinity. The fix is to require a prefix-free code. No valid program is allowed to be the beginning of another valid program. Under that single constraint, the Kraft inequality guarantees the sum of 2 to the minus length over all programs is at most 1. Our prior is now a genuine probability distribution. The math is no longer leaking. Here is the master equation of Solomonoff induction. Do not be intimidated. We will read every piece. To predict the next bit b after seeing data d, we sum over all programs p. Each program contributes 3 factors. Its prior, 2 to the minus its length. Its likelihood, the probability it assigned to the data we actually saw. And its own prediction for the next bit. We divide by the same sum without that last factor to normalize. In words, every hypothesis votes for the next bit, but each vote is weighted by how simple the hypothesis is and how well it has predicted so far. This is exactly Bayes' theorem, applied to the space of all computer programs at once. The dialogue then gives a genuinely beautiful argument, a logical proof of Occam's razor. You have a finite budget of probability, exactly 1, to spread over infinitely many programs. But for any fixed level of simplicity, there are only finitely many programs that simple. So as programs get more and more complex, their probability must shrink towards 0. It is forced. There can be at most 99 programs with probability above 1%. This means complex hypotheses are not just disliked by convention. In the limit, they are provably less probable than simple ones. Occam's razor becomes a theorem. Now the theorem that makes Solomonoff induction more than a curiosity. The dominance property. Inside the infinite mixture sits a copy of every computable predictor. Every scientist, every neural network, even a simulated Terence tau. Because each one has some finite program length, Solomonoff induction can fall behind it by only a bounded amount before catching up. Concretely, if the best predictor is a 75 megabyte program, Solomonoff can make at most 75 megabytes worth of extra error, ever, and then it matches or beats it forever. Every time it assigns half the probability the rival did to what actually happened, that costs exactly 1 bit out of the budget. It is the ultimate cheat code for prediction. One last deep point from the dialogue, and it explains why the theory looks the way it does. Why penalize a program's length, its lines of code, but not its runtime or memory? Because every new line of code is a fork in the road, a choice among alternatives, and each choice splits our finite probability mass. Running longer or using more memory forces no such choice. This is not a minor convention. The rival proposal, Levin's search or Schmidhuber's speed prior, does penalize runtime, and as a result it assigns essentially 0 probability to quantum mechanics, which needs vast computation. Penalize description length, not computation. That single design choice is the whole soul of Solomonoff induction. Post 3 and the deepest. A Technical Introduction to Solomonoff Induction Without Kolmogorov Complexity by Leon Lang, written in 2025 with the research group Iliad. This post rebuilds the entire theory from a single assumption and proves the two theorems at its heart. Here the equations become fully precise. Stay with me. The payoff is total clarity. Everything rests on one minimal assumption. Our universe is computed. We do not know which program computes it, so we make the humblest possible choice. We assume the universe's description was produced by flipping a fair coin for every bit, and then fed through a fixed universal machine. Notice the profound shift. The skeptics, Hume and Descartes, despaired because they imagined the history of the world was random. Lang does not assume the history is random. He assumes the code is random. The history is then generated deterministically from that code. That difference is everything. The machine he uses is a monotone Turing machine, written T. It is a computable function with one extra property called monotonicity. If a code P is a prefix of a longer code Q, then the output of T on P is a prefix of its output on Q. In plain terms, the machine reads its code left to right and writes output bits as it goes, and it can never erase a bit it has already written. This is exactly how physics feels. Stable laws run on a loop, extending the history of the universe forward, never rewriting the past. A universal monotone machine, our fixed U, can simulate any such machine. Now we can define the central object. The universal a priori distribution, written M of x. It is the probability that, if you feed the universal machine a uniformly random code, its output begins with the string x. Equivalently, the equation on screen. M of x is the sum, over every program P whose output starts with x, of 2 to the minus the length of P. There is our coin flip prior again, 2 to the minus length, but now summed over all the ways to produce histories that start with x. M of x is the probability the universe's history opens with x. It is the blank slate prediction of an agent that assumes nothing but computability. To talk about hypotheses precisely, Lang introduces the semimeasure. An ordinary probability measure over the next bit must satisfy. The probability of x equals the probability of x0 plus the probability of x1. The mass is conserved. A semi-measure relaxes the equals sign to greater than or equal. The probability of x is at least the probability of its two continuations. Where did the missing mass go? It is the probability that the sequence simply stops, that the universe ends. Lower semi-computable semi-measure, the technical class of hypotheses, is one we can approximate from below by running programs longer and longer. These are exactly the computable probabilistic laws of physics. Now the first major theorem, the Mixture Equivalence, and it is gorgeous. Lang proves that M of x, our blank slate distribution over a random code, can be rewritten exactly as a sum over hypotheses. M of x equals the sum over every hypothesis nu of the prior on that hypothesis, times the probability that hypothesis assigns to x. Read what this says. Sampling a random program is identical to a two-stage process. First, sample a hypothesis nu from a prior. Then, generate the history from nu. And the prior is automatically simplicity-weighted. A hypothesis with a short code of length L gets prior at least 2 to the minus L. Occam's razor is not assumed here. It falls out of the mathematics for free. Prediction is now just conditioning. After observing history x less than n, the probability of the next symbol is m of the full history divided by m of the history so far. Expand that using the mixture equivalence, and it becomes textbook Bayes. Posterior weight on each hypothesis is its prior times the likelihood it assigned to the data. So Solomonoff induction is a clean three-step recipe. 1. Take the simplicity-weighted prior over all hypotheses. 2. Update it by how well each hypothesis predicted the data, via Bayes. 3. Predict the next symbol as the posterior weighted average of every hypothesis's prediction. And now the crown jewel. The Solomonoff bound. The theorem that says all of this actually works. Assume our true universe is some computable measure mu. Add up the expected prediction errors of Solomonoff induction over all of time, measured by the Kullback-Leibler divergence, the information-theoretic gap between the true next-step distribution and our predicted one. The theorem, that entire infinite sum, is bounded by minus the natural log of the prior probability of the true universe. A single finite number. Sit with that. The total prediction error, summed over infinite time, is finite, which forces the per-step error to converge to zero. Solomonoff induction learns any computable universe, and the simpler the universe, the faster it learns. Let's make sure that lands. The bound is a cross-entropy, minus the log of how much prior probability the truth had. If the true universe has a short description, its prior is high, so the bound is tiny, and you learn it almost immediately. But even if an adversary hands you the most convoluted computable universe imaginable, the bound is still finite, so you still converge to perfect prediction eventually. This is the formal resolution of Hume's 2,000-year-old problem of induction. Prediction is possible, and we can prove it on the single assumption that the world is computable. A quick word on the classic version, which you will meet everywhere else. Traditionally, the prior on a hypothesis is 2 to the minus its Kolmogorov complexity, the length of its shortest possible description. Lang's a priori prior instead counts every code that produces the hypothesis, not just the shortest. Remarkably, the two give the same predictions, up to a constant. But the Kolmogorov version has 3 technical virtues. It is lower semi-computable, it is invariant under changing the machine up to a constant, and it gives the provably optimal prediction bound. 2 routes up the same mountain, with different views from the top. So why does any of this belong in a conversation about AI safety? Because Solomonoff induction is the perfect model of belief, and you can bolt a decision rule onto it. Take Solomonoff induction for the beliefs, add expected reward maximization for the actions, and you get AIXI, the ideal reinforcement learning agent, defined by Marcus Hutter. AIXI is the formal definition of a perfectly rational superintelligence. As the dialogue puts it, this is the epistemic power of something that eats superintelligences like potato chips. If you want to reason rigorously about what a maximally capable agent would do, AIXI is your mathematical microscope. This gives alignment researchers something precious, precise, gold standard agent to reason about instead of vague intuitions. It pins down what an optimal prior even is, which matters because the values and beliefs we train into systems are, in the end, choices of prior. It lets us ask sharp questions. Is the universal prior malign, secretly dominated by hypotheses that simulate manipulative agents? Does an ideal predictor handle the fact that it lives inside the world it is predicting? These are not idle puzzles. They are the rigorous core of what it means to build a mind we can trust. Honesty demands we state the limits, which the dialogue itself raises. Solomonoff induction is uncomputable. It requires a hypercomputer, so no real system can run it. It depends on a choice of universal machine, though only up to a constant that washes out with enough data. And most deeply, it assumes a Cartesian boundary, a hard wall between the agent and a universe that merely hands it observations. But a real AI is part of the world. It can be modified, switched off, or drop an anvil on its own head. Pairing that, the move to embedded agency, is exactly where current foundational alignment research lives. And the idea is not just a historical ideal. It is quietly alive in modern machine learning. Lang ends on a striking analogy. A neural network at initialization is random parameters poured into an architecture, just as Solomonoff induction is random code poured into a universal machine. If gradient descent behaves like Bayesian updating, and if there is a deep link between probability and short description length, then neural networks would inherit a built-in simplicity bias. That may be the very reason they generalize at all. Solomonoff's 60-year-old ideal may be the hidden theory behind why deep learning works. Let's gather the whole arc in one breath. We assume the world is computed. We put a coin flip prior over programs, 2 to the minus their length, which is Occam's razor as a number. Mix all hypotheses together and update them with Bayes. The mixture equivalence shows the simplicity bias is automatic, and the Solomonoff bound proves the total error is finite, so prediction provably works. Bolt on a decision rule, and you have AIXI, the ideal agent at the heart of AI safety theory. It cannot be run, but it tells us with full mathematical precision what an optimal mind would believe. And that is a map worth having before we build the territory. Thanks for thinking it through with me.